Welcome. So, we have learnt about the satellite communication, the core part of it, as well as certain issues that can develop out of that. Now, what we will discuss is one of the application, which is very interesting application, and most of us are using it daily. So, let us look at satellite navigation. Satellite navigation is the application of satellite communication. So, what will be covered today is what is meant by navigation as it is, and then how navigation is done using satellite, and estimation of position, time, velocity, how do we estimate that, basic functions of a global navigation satellite system receiver GNSS, and error and mitigation for the errors, and some existing satnav system, some description of that. So, first let us get into the definition. Navigation. What is meant by navigation? It is determination of position, velocity and time, three parameters. Three parameters are required. So, position is the values in preferred coordinate system. You can have a simple Cartesian coordinate system XYZ, you can have ECI or ECEF coordinate system. At the beginning of the satellite communication course, we briefly mentioned coordinate system. There are Keplerian coordinate systems, many coordinate systems. So, in a preferred coordinates, normally latitude, longitude, altitude is our preferred coordinate system. So, it will convert into that, but it could be done in any other coordinate system. So, that is the value of the position of the receiver. Velocity is velocity along the chosen coordinate, whatever coordinate we have chosen, and the velocity vector in that, and time is the universal time coordinate, UTC time. Now, in short, it is determination of PVT. The term what we use is PVT, position, velocity and time. Okay. Now, how do we do it with satellite? What is satellite navigation? That is any type of navigation that can be aided by satellite, and that satellite sends reference information to the user in coded from which the PVT estimations can be derived. So, satellites helps you to get the PVT estimation. Okay. A satellite gives you certain information, and from that information can be coded. From that you derive the position, velocity and time. So, that is the advantage of satellite navigation. Is obviously wide coverage. With a few satellites you can cover whole world, and there is disadvantage. We know its satellite is quite high above the sky. So, the signals which will be received at the receiver are very weak, and of course, it is passing, the signal is passing through ionosphere, troposphere, and these propagation impairments that can happen. So, these are the two disadvantages of that. Okay. So, there are four global satellite navigation systems popularly known. There are many. Some of them are operational, some of them are just starting to operate, or some of them are just upgrading themselves. The most commonly used and most commonly used as well as very popular system on satellite navigation is Global Positioning System, which is GPS. It is the US system. It is declared operational in 1995. Before that, some experiments were there, and International Civil Aviation Authority (ICAO) has declared that this could be an alternate civil aviation system. That is, while aircraft landing or taking off, the GPS system can be taken help of, in addition to the other systems what they have, ILS and DOR, VOR, etc. There is other one which is a Russian system, the Global Navigation Satellite System called GLONASS. It is operational, but not fully. They are upgrading it. And there is European system which is called Galileo. This is under development. A couple of launches have taken place. It will take a few more years to start operation. China has started launching some of the satellites for their system, which is called COMPASS. This is under development. It is not fully operational. These are all global systems. There are regional systems also. We will discuss about that later. Now, the architectural components of this satellite navigation system has three main components. One is the space segment, obviously the satellites, and the space segment has to be controlled by a segment which is called control segment, which are many earth stations which does certain measurements and upgrades the information to the satellite. And then satellite broadcasts those information about their location, and that is used by a user community, which is user segment. That can be, because it is position, velocity and time, it will be mostly mobile. The pictures are shown all mobile systems. It can be used for static purpose also. So, space segment consists of a constellation of satellites, not a single satellite, because it is a global system, it is a constellation of satellite, and provides necessary data for deriving the PVT information correctly. And control segment situated on the ground, multiple units are connected, they take certain measurements through a network, and then the space segment is monitored by the control segment. It predicts the ephemeris or predicts the orbit and update the necessary data to be transmitted by the satellite. The data is updated to the satellite by control segment, and also commands to maneuver the satellite if necessary to keep it in the orbit. The user segment consists of the users of this service. Users, you have to remember that this is a receive only terminal. There is some misconception many times people have. You know yourself only your position, velocity, time. It is a receiver only, it does not transmit. So, uses receive only terminals to receive the transmitted data from the satellite and compute its position, velocity and time. So, receivers are of different capabilities and different accuracies are available and used all over the world. Now, how do we estimate this parameter? That is interesting. We should know that how this parameters estimates position, velocity and time. The position is estimated using 3 reference positions in a 3-dimensional system, x, y, z. Let us take x, y, z coordinate with a center point at center of the earth. So, 3 reference positions, that is, reference positions are 3 satellites. They at that instant of time it is reference. So, 3 reference position for a 3-dimensional system and derived using distance from the reference location. The user who is receiving this reference position, how far away from each reference position it is. So, that is distance once it is known, once it is measured, observed, and then position can be derived. Okay. Time is a reference time, which is UTC, and that is derived using the elapsed time from the reference instant. At the user, when it receives, it can estimate what is the time when it has received in terms of UTC and convert into the local time. And velocity is derived from the position, velocity and time. This is velocity is derived from the position and time, that is derivative of that, or using a Doppler technique. So, these are the 3 methods. We will go into a little more detail of estimation of position. Position estimation, it is estimated in the 3-dimensional space, 3 coordinates, that is x, y, z. Knowledge of 3 reference position and the corresponding distance from the reference location, that is important. So, this technique is called trilateration, not triangulation, which is done in the normally survey work. Here it is trilateration. What is trilateration? It is the estimation of a position unambiguously based on measurement of distance from known reference locations. For 3-dimensional system, it is 3 known reference locations, and if you know the distance between them, so you get a trilateration. Let us try to understand easily. Let's assume that each satellite is as isotropically radiating all sides. So, the radiations of signal is spreading like a sphere, and another satellite is also at the same time is radiating, is spreading like a sphere. So, these 2 spheres will cut or cross themselves in a circle plane, in a circular plane. And then if there is a third satellite which is also isotropically radiating at the same time, so that will cut into 2 points. So, intersection of the spheres are at 2 points. So, if you know the positions of these, you will really position of these reference satellites, you know really your position can be one of these 2 cut points. So, whichever is nearer to earth, that is taken, that is one of the method. So, how do we? So, 3 equations are required to solve 3 unknowns, it is known, and 3 quadratic equations formed using 3 reference positions and corresponding ranges. And these quadratic equations are based on measured distance, which is called observed distance, or it is called observable equation or observation equation. So, 3 observation equations for 3 satellites could be simple, our geometry. R1 is that observable, that is the distance, is root over of x s1 minus xu whole square plus y s1 minus yu whole square plus z s1 minus zu whole square, where s stands for the satellite, 1, 2, 3 are 3 satellites, and u is the user positions, that is x si, y si and z si are ith satellite coordinate, that is 1, 2, 3, and xu, yu, zu are unknown user positions. So, if the x si, y si, z si are known, which is broadcast from the satellites, individual satellites, and if we can observe or measure this R1, R2 and R3, then our unknowns are xu, yu, zu, 3 equations, it can be solved easily. So, above simultaneous equations are solved to get the unknowns, which are xu, yu, zu, but it is quadratic equation, remember. So, there are 2 possible solutions that will be coming. So, with 3 satellites position determined with ambiguity. So, there is ambiguity due to quadratic nature of the observation equation. Now, using a linearization approach, only 3 equations could be sufficient for solving 3 unknowns. This is some approximation approach, Taylor series approach. Then 3 equations can be used to solve 3 unknowns. But there is a but, we will see later there are 4 satellites and 4 equations are required for some other reason, we will see that one. First, let us see how we do the linearization. So, reference positioning, locating the position of the reference satellite, it is done using ephemeris of the satellite. Now, these ephemerides are Keplerian parameters, which are if you remember at the beginning of our course we talked about eccentricity and then inclination, then the semi major axis, like that. There are 6 Keplerian parameters that defines a satellite in a orbit, satellite position in a orbit. It can be translated or transformed into other coordinate system. So, satellite transmits Keplerian parameters of their position at a particular time instant. These satellite ephemerides are estimated at the control segment. Why it is estimated? Because satellites might be drifting from its orbit a little out because of sun moon drag, earth drag, we have discussed this one earlier. So, this ephemeris at a particular instant, when it is visible to the control segment, the control segment calculates its exact ephemeri at that instant, uploads, and the next time when it visits the control segment, it will give the correction to it. In between there will be a little more drift, so that has to be modeled. So, let us for the timing assume that ephemeris at each instant are available at the satellite, which is uploaded by the control segment for every orbit, it is corrected. Satellite broadcasts these ephemeris to the user at a particular time, at that instant of time. So, that means satellite sends certain message down to the earth, each satellite. Now, user derives the satellite ephemerides from the corresponding navigation message. So, the navigation message which is broadcast from the satellite, from each satellite is broadcast identified, and so user try to derive the satellite ephemerides. Their broadcast message contains many other things which we will see later. So, it will take out the ephemerides, and then then using the satellite position at any instant, receiver can calculate the range up to that satellite at that instant. What was the range from the satellite to the user? How do you do the range estimate? Because it is the only one way. If you remember, if you recollect in our telemetry telecommand discussion, we did some ranging, and that ranging was a two-way ranging. It is full loop. A tone was sent or a PRBS sequence was sent to the satellite, satellite downlinks them. So, a two-way ranging, in that we estimated the range. But here it is only one way, because the receivers, the user receiver, GPS receiver, GNSS receiver, it is receive only, it does not transmit. So, it has to be a one-way ranging. How does it done? How do we do it? So, this ranging is a measure of distance of the user from each reference point, that is the satellite. Range is obtained using a time of arrival technique of the or the total time taken by the signal to travel from the satellite to the user. Okay. Total travelling time of the signal is obtained from the difference between the time of transmission and time of reception. It is simple. Pictorially, say at t equal to t1 the satellite transmits, and at t equal to t2 the receiver receives it. Assuming the signal is travelling with the velocity of light c, r is equal to c into t2 minus t1. Okay. t1 is the time of transmission of the data from the satellite, t2 is the time of reception of the same data, t2 minus t1 is the time taken to propagate, and assuming c is constant during propagation, c is equal to t2 minus t1, which is the estimated range. Now, how do you know exactly what time it has transmitted? So, therefore, digital codes are used. Digital codes are used with a sequence, a unique type of sequence, let us say, or PRN sequence. The code is transmitted from the satellite. Let us say this code is 10101110, like that, a code. Now, that is transmitted at an instant t1, and this code is received after certain delay. The code has arrived, that is at this point t2, t1 it was transmitted, at t2 it is received, that is 10101110, like that. Now, receiver locally generated the same code, and that is 1010 locally generated, and that code is shifted and compared with that. So, when the autocorrelation works, when it is properly correlated, you find out the shift in time or shift in number of bits. So, that is delta t. So, once you know the delta t, that is t2 minus t1, you know the range, assuming velocity of light is travelled. Now, there may be some errors. So, if there is a reference station, reference satellite R3 has a error epsilon, each of them I assumed error epsilon same. So, the position will be with some inaccurate position, okay, with some region, it may be anywhere, the A is may be anywhere from 3 satellites it is transmitted, the dotted lines say certain errors are there. So, uncertain position at A due to range estimation error. Why this uncertainty? Certainly, I talked about. Let us see. The at Ts, I am slightly changing the nomenclature. Ts is the capital Ts is the time when the satellite has transmitted, and capital Tu when the signal is received at the receiver. So, delta t, that is Ts minus Tu, is the true time difference. From that you can find out the range. But these times are derived from some clock by cycle counting, and that clock may have some error, some instability. We have talked about it earlier. So, that let us assume satellite clock error is del t. So, Ts plus del t actually it was transmitted, it may be minus also, and at user also has a clock which is a different clock, physically it is a different clock and different stability. So, it let us have a small t u its stability, its error. So, it is received at capital T u plus small t u. So, you get a time difference which is not same as delta t 2 time difference. So, it is with error. So, geometric range, the correct range should have been r is equal to c into t u minus t s is c into delta t, whereas we get a range which may not be correct, which is called pseudo range. The word is pseudo range, we call it rho. Rho is c into capital T u plus small t u, that is the user clock drift, minus capital T s plus del t, that is the del t is the satellite clock error. So, the time shifted from that. So, because of these two you get true range plus c into t u minus del t, which is that is you can change the side and you can find out what is the true range. R is equal to rho minus, that is pseudo range, minus the c into the clock differences between the two stations, one is user receiver, another is satellite. So, but at the satellite people use atomic clock. So, del t is negligible, del t is negligible. So, therefore, rho minus c into t u, that is user clock error, that is the time error, is equal to the range. Del t is put as a negligible. So, all this type of navigation satellite carry atomic clock, that is complexity increases in the satellite, but your calculation becomes much easier, calculation of the range becomes easier. Okay. Now, say I am telling the same thing again. T s is derived from the satellite clock. It is an atomic clock of the very high stability cesium clock 10 to the power minus 13. We know what is stability of clock, we have discussed earlier, and T u, that is capital T u, is obtained from the receiver clock. Its stability is much lower, of the order of 10 to the minus 6 to 10 to the minus 9, depending on what type of receiver it is, and the receiver clock drifts with respect to satellite clock. So, causes clock offset error leading to erroneous estimation of the delay. So, the erroneous ranging, once the delay estimation error, ranging estimate also will be error. So, this is a variable thing, this difference of the clock offset, and this is unknown also. So, therefore, we can use another equation, that is receiver clock offset, also taken as unknown for solving the position, thus requires an extra observation. Now, you know why 4 satellite observations are required, or 4 equations are required. So, we can write it as a rho j, which is the j is 1 to 4, that is 4 satellites, that is the pseudo range is root over of x j minus x u whole square, y j minus y u whole square, plus z j minus z u whole square, plus c into t u. Okay. Now, how do you find out the solution? Solution for the unknowns obtained from the 4 observation equation solved using a technique which is called linearization. Most of you know about it. So, linearization is a technique to linearize equations about approximate position, that is initial guess. You guess that this could be my position, and the solve it iteratively. So, you improve, go on improving the guess, that is the thing, and you remove the higher order terms. So, method uses the a priori approximate knowledge of the solution and then solves it iteratively. It reduces the quadratic equation into linear equation, and it reduces the problem arising of the nonlinearity, and it is less computational intensive because quadratic part is not there. Let us say, how do you do it? Let us say this is the satellite, this is a user position, and this is the pseudo range, and we estimate at rho cap j, which is the estimated range, that is a red dot. So, it is away from the true range by del x u, del y u, and delta z u. This by these 3 vectors it is away. So, true range and estimated range, and these are the displacement from the true position. Del x u, del y u, delta z u is displacement from the true position. Okay. Remember this figure. Now, let the pseudo range is equal to, we have seen this equation, it can be written as a function of x u, y u, z u plus t u. Using approximate location, x u cap, y u cap, z u cap, and time bias also approximate t u cap, we can put x j minus x u cap whole square plus y j minus y u cap whole square plus z j minus z u cap whole square root over of that plus c t u cap, which could be function written as function of x u cap, y u cap, z u cap, and t u cap. Okay. So, as this you try to remember the vector. So, the x u is x u cap plus del x u, this is a true position, this is approximate position, and this is displacement. Similarly, y u, z u, and t u also. So, the equation can be written as a function of x u, y u, z u, t u is function of x u cap plus del x u, y u cap plus del y u, like that, and differential equations can be formed out of it, and there will be higher order terms. Now, we can neglect this higher order term because they are very small. So, how do we derive this? you see this is a true range, this is the true pseudo range, we will call true pseudo range, okay, a pseudo range, and this is the approximate pseudo range. So, difference of these two are all these differential terms. Now, this difference between the pseudo range and approximate pseudo range can be expressed as delta rho j as coefficient a x j delta x u, a y j delta y u, a z j delta z u minus c into delta t u. Assuming coefficients of this a x j, a y j, a z j etc. as H matrix, this can be expressed in the form of matrix from del rho is H cross delta x. So, delta x can be found out by H inverse, a matrix solution. Now, once you know that the delta x are calculated, user position and time can be calculated using our original expression, that is x u is this approximate plus now you have found out delta x u, delta y u, delta z u, delta t u. So, you find out this, and then this technique works well when the estimated position is near the actual position. When the displacement is more, user acceptable accuracy requirement threshold, then new set of estimated value are taken and the process is repeated. Okay. So, since the time is up, we will continue this discussion in the next session. Thank you very much.